Many enzymes recognize their substrates through docking interactions. These docking interactions are often separate from the catalytic domain and are thus structurally independent of the enzyme mechanism, thus modular. It has long been believed that such docking interactions should ideally be of intermediate strength. But what does intermediate strength mean? This is the question we're asking in this paper, where we try to define the optimal docking interaction for a kinase domain tethered to its substrate.
We use a model system consisting of a kinase domain tethered to its substrate via intrinsically disordered linkers and a coil-coil interaction. This allows us to change the length of the linkers and the quality of the substrate independently. We tune the strength of the docking interaction through mutagenesis. By combining 3 well-chosen mutations, we can vary the strength of the docking interaction by more than 1,000-fold while keeping all other parameters constant. Then we tested the ability of these docking interactions to enhance the steady-state phosphorylation rate. We find that the phosphorylation rate has a bell-shaped dependence on the docking strength, with an intermediate strength providing the optimal enhancement. The position of the apex and the magnitude of the enhancement depends on the substrate concentration, the substrate quality, and the length of the linker. We can reproduce the behavior of this system using numerical simulations. This allows us to study a much broader parameter range than we can study experimentally. We also develop an analytical equation that allows us to predict the optimal docking strength as a function of the properties of the enzyme and the nature of the linker.
This allows us to deduce general design principles for when an enzyme reaction is enhanced most by a docking interaction. We find that the docking interaction is most efficient enhancing the enzyme when the binding strength is intermediate and the binding and dissociation kinetics are rapid. We find that the enhancement is largest when the substrate is relatively poor and present at low concentrations, and when the linker architecture maximizes the effective concentration of substrate presented at the active site.